So this talk will be somewhat similar to a talk I gave this summer in virtual Canada at a birds workshop that Hans was also a part of. So, and it's a great pleasure to be able to tell you about this, and it's a joint work with Catherine Rayox. Okay, so the yeah, as I indicated in the title, this is about relative adjunction inequalities. And in this context, their role as a tool for studying link concordance, because in light of the theme of the workshop, so I'll focus on this on these aspects of them, whereas in some other talks maybe I'd emphasize some other usages of the relative adjunction inequality. But before I get into link concordance, I want to just set the stage with the kind of general question that adjunction inequalities are designed to handle, and this is the minimal genus problem. So the minimal genus problem says, so suppose I'm given a second homology class. And perhaps a relative second homology class where X is some manifold, maybe smooth, maybe topological. And the minimal genus problem asks to determine the genus of that class, which I'll define to be the minimum of the genus of any surface embedded in the manifold X. If the manifold, if I'm talking about a relative homology class, then I'll maybe be considering surfaces with boundary whose boundary maps into the subspace Y, such that their fundamental class of the surface represents the given second homology class. So here I'm considering clearly, or hopefully clearly, orientable surfaces, although you can make sense of this for Z2 homology classes in the non-orientable situation. And so my focus today is going to be where X is a smooth four manifold and where the surfaces in question sigma are smoothly embedded. But there's a lot of variance to this question. You can think about it in other dimensions. In dimension 3, this turns into the well-known problem of ascertaining the Thurston norm of a 3 manifold. And in higher dimensions, there's I think still interesting questions probably that can be had in certain contexts. And of course, in dimension 4, there's a big distinction between asking this question when sigma is supposed to be smoothly embedded versus, say, topologically locally flat. So the regularity of the embeddings is quite important for the outcome. Okay, so sort of guiding example of this problem is the so-called Thom conjecture. And so the Thom conjecture asserts that the minimal genus problem is solved for the complex projective plane by smooth complex curves. So it says that if you have a smooth complex curve in the complex projective plane, then it minimizes genus in its homology class. And this theorem was originally proved by Kronheimer and Rufka using Seiberg-Witten theory and gauge theory, and it had a number of antecedents in the context of Donaldson theory. So this is Kronheimer and Rufka. And later, Ojvad and Szabo extended this to the context of more general symplectic four manifolds, and they proved what's known as the symplectic Thom conjecture, that says that symplectically embedded surfaces in a closed symplectic Floer manifold likewise minimize genus in their homology classes. And the key tool for all of these results is the so-called adjunction inequality. Junction inequalities. And so I'll state a version of this. So let's let X4 be a smooth, closed Floer manifold. And equipped with a spin C structure, which I'll denote by T. And if you have a spin C Floer manifold, then you have an associated Seiberg-Witten invariant. And I'll assume that this invariant is non-trivial for this particular spin C structure and Floer manifold. Then the junction inequality gives us a bound for the genera of surfaces in a given homology class. So it's phrased in terms of the evaluation of the Chern class of the spin C structure, which is a two-dimensional cohomology class, on a homology class of a surface, coupled with the self-intersection of the surface. And the junction inequality says that some of these quantities is bounded above by negative the Euler characteristic of the surface. So this is where sigma is any smoothly embedded surface. And here in the version that I'm stating right now, I'm assuming that the self-intersection is non-negative, although this can be extended to surfaces of negative square as well, but with some cost at the at the cleanliness. Okay, and so my goal today is to first tell you about a relative version of this of the minimal genus problem and the corresponding adjunction inequalities that can help solve it. And there are sort of two different things I might mean here. One is I could think about relative homology classes in for a Floer manifold with boundary where they're relative to a knot K or a link in the boundary of X. And another question that I might ask is I can think about just relative homology classes sort of where the boundary conditions are much more flexible, where I just say I want to look at relative homology classes whose, sort of look for surfaces whose boundary lie in the boundary of the manifold. And my focus today is going to be really on this problem. And so some of our more recent work that I won't have time to tell you about maybe has something to say about this, but the jury is still out. And as far as I know, really very little has been done on this latter problem. So I think it's kind of an interesting question. Solve, understand a minimal genus problem in certain examples for relative homology classes on Floer manifolds with boundary. Essentially the only ones that I think have been studied are the places where A such that under the boundary homomorphism in the exact sequence, this goes to 0. So essentially, this tells you that they lift to absolute homology classes. So you're really studying the original problem. So I think it'd be very interesting to study the latter, and we might have some tools to do it finally, but I won't be able to tell you about them today, I think. Okay. Right, so the key tool that we're going to use to set this up is not Floer homology. So essentially what not Floer homology is going to do is going to provide some numerical invariants that'll refine the adjunction inequality for closed manifolds that I stated. So let's just, so a quick recap then of the last 20 years of Heegard-Floer homology. Wow. as I need it. So if I have a closed oriented three manifold, we can present this three manifold as a Hegardt splitting. So that's to say I have a closed oriented surface sigma embedded in the three manifold that separates the three manifold into two handle bodies. And given a Hegardt splitting of that form, I can represent it or encode it with a Hegardt diagram, which consists of that same surface together with a collection of G, where G is the genus, homologically linearly independent simple closed curves on the surface that bound disks and the alpha handle body, or in one of the handle bodies, which I'll call the alpha handle body. And likewise, a collection of curves on the surface denoted beta 1 through beta G that specify disks in the other handle body. And then there's also going to be a base point W in the complement of those curves. And so this is a Hegardt diagram. It's a way to encode a three manifold, well, in reality, a pointed three manifold, where that base point plays a non-trivial role in the theory that was understood somewhat after the fact by Juhas, Thurston, and Zemke. So, okay, so given that data, we can then use this to port in a symplectogeometric construction called Lagrangian Floer homology. And so associated to this data, we'll consider the Lagrangian Floer chain complex. So these are associated to a pair of half-dimensional submanifolds of the so-called symmetric product of the surface. So the surface, of course, is a two-dimensional oriented real manifold. I can consider G tuples of points on that surface. So unordered G tuples of points, some of which may be the same. This is a 2G dimensional, as it turns out, Kähler manifold, and so and hence symplectic. And so I'm going to take that manifold and I'm going to remove from it a real codimension 2 submanifold specified by that base point. So this manifold BW is the set of G tuples of points, at least one of which is the base point W. So this is an open symplectic manifold, and it has sitting inside of it two half-dimensional submanifolds, each diffeomorphic to real G-dimensional tori, denoted T alpha and T beta. And these are tuples of points, all of which lie on the alpha curves or beta curves, respectively. Okay, and so from this, so what Floer defined associated to this setup is a chain complex generated by intersection points of the two submanifolds, and whose boundary operator counts J holomorphic curves or pseudo holomorphic curves connecting the two various intersection points. Okay, and so this this complex in this context is denoted CF hat of Y. It's called the hat Hegardt Floer chain complex associated to Y. And a fundamental property of this, which relies on, again, on this base point, is that the complex admits a splitting, a direct sum splitting along spin C structures on the three manifold. And perhaps miraculously, the homology of this, perhaps miraculously, this is a chain complex, and moreover, its homology is an invariant of the three manifold, or of the spin C3 manifold when you think about the splitting. So for those new to spin C structures, you can always just think of these as second cohomology classes. There's a non-canonical bijection between them. Okay, and so now if we have a knot inside a three manifold, this whole process is refined in a very beautiful and useful way. So suppose I have a knot K inside my 3 manifold. Well, you can encode a knot inside a 3 manifold by finding a particularly nice Hegarde decomposition adapted to it, where the knot is encoded with a pair of base points. And that pair of base points specifies a pair of properly embedded arcs in the 2 handle bodies. So we have 2 unknotted arcs in the alpha and beta handle bodies, respectively. So I'm just going to mess up my picture so it looks totally messy, but you can imagine that this is understandable. So so you can specify a knot with a pair of base points. And what this does, what this does is it endows our chain complex with an additional structure. So this chain complex further splits via relative spin C structures. So relative spin C structure now is in affine correspondence with relative cohomology. So if you think Poincare dually or Lefschetz dually, this is H1 of y minus k. So if you think to the 3-sphere, the 3-sphere has no second cohomology, so there's only one spin C structure. But when I remove a knot, say, from the 3-sphere, the first homology of the knot complement is Z. So you have a Z worth of relative spin C structures, and hence you get this kind of refined splitting of the Hegarde-Floer chain complex, or refined grading on the Hegarde-Floer chain complex. Okay, so relative spin C structures are beautiful, but it's nice to be able to have a more concrete understanding of them, and turn this splitting into an additional grading, grading by numbers on the complex. So given a relative homology class of a ciphered surface, I can define a grading called the Alexander grading on this complex. And the way that we do it is, given one of these intersection points of my Lagrangian tori, I can consider, well, a relative spin C structure has a relative first term class, which is a relative 2-dimensional cohomology class. And so each intersection point that generates my complex gets associated this relative spin C structure, and I can take its Chern class. That's a relative cohomology class. And I can evaluate this on the relative homology class of the ciphered surface that I've chosen. And then so that I get an integer, I add to this the intersection of the ciphered surface with the meridian of the knot. Okay, so that's 1 for the moment. So this is now some integer, once I divide by 2. Okay, and then what I can use then, so it's now I can use this grading to associate numbers to knots. So given your favorite Floer homology class, say non-zero Floer homology class, and the Hegarde-Floer homology of a 3-manifold, and a knot inside Y, I'll define tau alpha yk to be equal to the minimum Alexander grading of any cycle representing my given class alpha. So this is now some number. Okay. Now you see at this, in order to employ this construction, I've used a ciphered surface, and there's some dependence on the ciphered surface here, or at least its relative homology class. But we don't actually need to have a a ciphered surface, but in order to use it, we can get by with just a what's called a rational ciphered surface. So if the knot is rationally null homologous, which just means that its homology class vanishes in H1 of Y with rational coefficients, well, then some multiple of it of its homology class will bound a surface, and so I can take a Q ciphered surface. Maybe I should do this in pink. So this is a refinement in the case that the knot is not null homologous, but only rationally null homologous. And then the modification here is that, you know, the rational ciphered surface, its boundary is not equal to the knot because the knot has no ciphered surface, but its boundary will wrap some number of times around the knot, say given by the order of its homology class. So what I do then is I divide these terms by the order of k. And so as a result, this is no longer an integer, but this is a rational number. So associated to null homologous knots, we get integers, and associated to rationally null homologous knots, we get rational numbers. Okay, and so the question then is, what good are these numbers? And the kind of general answer is provided by the following theorem. Just joint with Catherine. And there's an alternative proof that can be deduced from the grading shift formula and Zimke's work on link cobordisms and the null homologous case. And so the theorem says that if I have a smooth cobordism between two manifolds from manifold Y1, 3 manifold Y1 to Y2. So I want to have some Floer homological assumption that mirrors the non-vanishing of the Seiberg-Witten invariant in the closed case. And that's going to be provided by the following condition on a cobordism-induced map by a spin C structure on that cobordism. So if I have a spin C structure on the cobordism for which an associated map on the Floer groups maps a given Floer class alpha to beta, then I have the following junction inequality. So I have this inequality for any smooth cobordism sigma smoothly embedded in W from a knot K1 to K2 in the boundary. So you'll notice that I could actually put absolute value around the Chern class evaluation to make it look even more similar to the junction inequality for closed manifolds due to conjugation invariance. But you'll notice that the key difference is that the tau invariants that we just defined, these numerical invariants of knots, play this kind of correction role in the adjunction inequality, which in general will sharpen it considerably. Okay. So maybe before I sort of give a picture of this, maybe I should remark that sigma is an H2 of W rel boundary. So sigma doesn't actually have a self-intersection. That's it doesn't make sense to talk about sigma squared. And C1 of a Chern class, the Chern class of a spin C structure is a two-dimensional absolute cohomology class. So this evaluation also doesn't make sense. But so so if I look at the relative homology class of that surface of a cobordism between knots, this will go to the class of K2 minus K1 inside first homology of the boundary. And so I'm assuming that these knots are rationally null homologous. So that allows me then to lift this class to an absolute class, which I'll denote sigma tilde. Now the question arises, I mean, how do I, what's the dependence? How many lifts do I have? And I have as many lifts as I have two-dimensional homology classes of my boundary. So in order to specify a lift, this is specified by rational Cipher surfaces. S2 and S1 for K2 and K1 respectively. So I can think about this geometrically maybe as 1 over D1, where the D1 is the order of K1 times a rational Cipher surface for K1 union sigma union negative 1 over D2 times S2. Okay. I mean, so, if there's one thing that I've learned from this project is that, the kind of numerology that that comes up when you're dealing with rationally null homologous knots in the context of Hegardt-Floer homology can get a little bit tricky. But I think one thing to sort of take away, if you ever sort of, tempted to move in that direction for some reason, is that, you should try to not actually think about rational Cipher surfaces. You should stop thinking so geometrically and just think about rational chains. Everything gets much easier if you just say, oh, I'm just going to take, a rational two chain whose boundary maps to the knot. And then, so it's not actually a surface. It's like it's 1 over D1 times the surface, and things everything gets way easier. So, okay. Right, so now the terms in this make sense, and let's draw a picture of the situation and sketch the proof. So here's a literal sketch. The situation that we're dealing with is I have this surface, it's a cobordism, or this cobordism W. And inside it, I have a cobordism between knots K1 and K2. So the idea is that I'm going to attach two handle cobordisms to both ends. So I'm going to attach two handles along Y1 and Y2 attached along K1 and K2 respectively. So this is on the right hand end, on the outgoing end, I'm going to attach the two handle cobordism with framing some large negative number N attached along K1. And on the left-hand boundary, I'm going to attach the two handle. I'm going to attach a two handle with framing M, where M is positive. But I'm going to reverse its orientation. So this is still a negative definite two handle cobordism. And so it's then viewed as a cobordism between M surgery on K2. And I have my indices backwards. M surgery on K1 and the manifold Y1. Okay, so so the ingredients here for this proof is that tau alpha Y1 K1 controls when the associated cobordism map to that two handle that I've attached maps onto alpha. And on the other end, tau beta of Y2 K2 controls when the other cobordism maps beta non-trivially. And the way in which it controls it is that you can enumerate spin C structures on those two handle cobordisms by Chern class evaluations. And in terms of that numerology, we can understand when specific spin C structures on those cobordisms map alpha, map to alpha, or map beta non-trivially, respectively. So then, by assumption, my cobordism equipped with a particular spin C structure, T, maps alpha to beta. And so I can use my knowledge of tau to tell me exactly which spin C structures will have the property that they'll exist in alpha tilde mapping to alpha on the left end, and a beta tilde mapping from beta on the other end. So I can use this knowledge to produce a non-trivial cobordism map for this extended cobordism. And once I do that, I'm going to factor my extended cobordism by capping it, capping the surface sigma with the cores of the handles that I've attached. So now I have a closed surface of the same genus capped off with the core disk of the two handles. And I'll take a neighborhood of the incoming boundary and join it up to that neighborhood of the surface. And I'll call that whole configuration N. And so then the next ingredient then is we need an adjunction inequality. For this cobordism N. And so in order to prove that, one thing we use is a kind of Kuhn theorem. For cobordisms under an operation we call arc sum. So if I have properly embedded arcs in two Floer manifolds with boundary, I can take a neighborhood of those properly embedded arcs and glue them along the resulting S2 cross an interval. And so the kind of Kunith theorem for connected sums of three manifolds has a sort of functorial interpretation with respect to those types of cobordisms. And we use that to get this adjunction inequality for n, and then use the composition law for cobordisms. So if I think about this cobordism, the extended cobordism is, so I can factor the cobordism map FW is equal to F, or extended cobordism is F n composed with F W minus n. Okay, and so using that together with this vanishing result or adjunction inequality for the cobordism n allows us to arrive at the stated inequality, with kind of the key feature being, how do these Chern class evaluations sort of decompose when I look at this extended cobordism? So key feature is, we sort of split this surface sigma into pieces where I attach S1 and minus S1 here homologically, and S2 and minus S2 homologically there. Okay, so that's the sketch of the proof. Okay, right. So, are there any questions before I move on? I want to talk about some examples of applications to this.
Can you put up your theorem again, the inequality? I was wondering where the complexity of W comes in, because if W has like a lot of two spheres embedded, that you could connect some to this cobordism, how do these terms in the inequality change? And maybe another special case, what if this W is really just a product cobordism?
Yeah, so I'll state that specific one in a moment. And it's true that the topology of W plays a big role. I mean, where it's coming into the picture is in this assumption. Different cobordisms will have different interaction with the Floer homology of the three manifolds on their boundary. And so, for instance, if you were to say, take the internal connected sum with S2 cross S2, that has the effect of killing all of the invariants here. And hence, we won't be in a position where we can actually use this as use the theorem. So there are certain operations you can do on Floer manifolds that'll kill the Floer manifold invariants, and then we'll not have we'll have sort of vacuous understanding with respect to this inequality. But it's a good question as to, so in what situations are we able to use this? When do we understand the maps induced by cobordisms on Floer homology? And so the first example where we do have such an understanding was where Y is the three-dimensional sphere, and say the Floer manifold is the Floer ball. And this was a case handled by Ojvat and Sabo and independently by Rasmussen. The Floer homology of the three-sphere is very simple. It's just a, say, Z2 vector space of rank 1. And so there's really only one non-zero class that I can pick, and I get this invariant which they call tau. So, and this is a number. And so what they use this to show is that, so for instance, in this case, the relative invariant of the Floer ball is equal to, say, generated by theta. Maps to theta non-trivially, and so you can use this inequality to show that tau of k is less than or equal to the genus of any surface embedded in the Floer ball. So this says that tau bounds the Floer genus, and you can because B4 has an orientation reversing diffeomorphism, I can get an absolute value around this. I can apply it as a cobordism in both directions. Okay. So maybe as a word of convention that if I have a four manifold with only a single boundary component, then what I'll do is I just puncture that cobordism and regard it as a cobordism from the three sphere to the boundary. And then there's only one class, the element one, that I can consider in the incoming boundary. So now let's think about maybe the next simplest four manifold, and this is the one you brought up. Consider the product cobordism y cross I. So the map on Floer homology associated with product cobordism is equal to the identity on the Floer homology of y. So this is, in some sense, the best possible case, because now this is an extremely non-trivial map on Floer homology. It's as non-trivial as I'm going to get, in some sense. So what I get from this then, so this implies every alpha in the Floer homology of y is in the image of f cross I. So what I get from that then is that I get genus bounds similar to what we had for the initial tau invariant for the three sphere, namely tau alpha yk in absolute value is less than or equal to, let me just call it the y cross I genus of k. So the minimal genus of any smoothly embedded surface in y cross I whose boundary maps to k. So another application of this in this setting is that if K1 and K2 are concordant, so that's to say that there's a smoothly embedded annulus whose boundary maps to K1 and K2 and Y inside, so smooth and properly embedded annulus in Y cross an interval, then tau alpha yk1 tau alpha yk2 for every class in Y. And so in some sense, then the product manifold is the place where you get the absolute strongest information about smoothly embedded surfaces from these inequalities. And that really shouldn't be a surprise to us, because you know that if there's any four manifold, by the Collar neighborhood theorem, you know that there's a neighborhood of the boundary where that looks exactly like y cross I. So if you have a surface in y cross I, it's going to induce a surface in an arbitrary four manifold that contains y in its boundary. So you should expect these to be stronger than any other genus bounds that I would get. Put differently, the more topology that a four manifold has, then the more likely you are to slice a given knot. And a final application in y cross I is you have crossing change inequalities. So tau alpha of yk plus, let's say yk minus. So if I have knots k minus and k plus that differ by a crossing change, and I have this sequence of inequalities. For every alpha. Okay, so great. So I mentioned that we'll get link concordance invariants, and I'm running out of time. So how are we going to get these? Particularly, oh, okay. Thought that my screen had frozen. So the next simplest example of a four manifold, maybe a four manifold is obtained from the four ball by attaching one handles. So so if I look at y equals S1 cross S2, the Floer homology of S1 cross S2 is two-dimensional and supported in gradings -0.5 and 0.5 respectively. And both of those generators of both of those two summands are in the image of particular four manifolds. So I can look at S1 cross D3, puncture it to view it as a cobordism from the 3-sphere to S1 cross S2. And this cobordism maps to theta 1/2, maps to the upper generator, and S2 cross D2 maps to the lower. So this says that tau plus, which I'll denote, that'll be the sort of tau relative to the upper generator of a knot in S1 cross S2, is less than or equal to the genus of smoothly embedded surfaces in S1 cross D3, and tau minus is less than or equal to S2 cross D2. And there's an inequality between these two invariants. So of course, if I have a surface inside of S1 cross D3, I can perturb that surface so it misses the circle. And then I can surger the circle to get a smoothly embedded surface in S2 cross D2. So I have this kind of topologically defined inequality obtained by surgering the circle in S1 cross D3. And there's a corresponding inequality between the tau invariants. And this is a manifestation of an inequality for the tau invariants of the form, if you have a given Floer class, in this case, the Floer class in bottommost grading, which is in the image of the action on Floer homology by elements in H1 of the 3-manifold. In this case, you have a non-trivial action on Floer homology, sending the upper generator to the lower. Then you get an inequality between the corresponding tau invariants. So there's kind of a monotonicity with respect to the H1 action for these tau invariants, and that reflects this this geometric inequality for the slice genera. And you can use these inequalities for S1 cross S2 and their connected sums to obtain link concordance invariants. And so the idea is that if you have a knot in a 3-manifold, or sorry, a link in a 3-manifold, you can turn it into a knot in that 3-manifold connected sum with a number of copies of S1 cross S2, one fewer than the number of link components. And the basic idea is this process is fuse the components inside one handles attached to Y cross I. So if I have, say, a 2-component link such as the hop flank, I get a knot inside S1 cross S2, which attaches a band to fuse the two links together, or the two components together, but this is clearly not well defined in general. So I can make it well defined by doing it inside of a one handle. So I get a knot now in S1 cross S2. And say in this case, so in this particular example, the notification of the hop flank has the property that tau plus of kappa of L is equal to 1, tau minus a kappa L is equal to 0. And so this reflects the fact that the notification, this does bound a disk in S2 cross D2 doesn't bound a disk in S1 cross D3. And so the key features of this process are that then I get invariants, one for every Floer class in S1 cross S2, or the connect sum thereof. And I'll define those to be tau theta of L. And for any theta, tau theta L is a concordance invariant of the link inside the 3-sphere. Bounds the slice genus detects fibered knots or strongly quasi-positive fibered knots. And has a number of other properties in line with many of the properties that we understand for tau of knots in the 3-sphere. And I should maybe mention that many of these properties have been explored for, on the face of it, different invariants by Alberto Cavallo and Ojvat Szabo Stipschitz in the context of grid homology for knots and links. And the invariants that I'm defining here, we've shown agree with them. So it's, there's different ways you can view this. I mean, ours have this kind of nice feature that they're a bit more geometric and we can understand them for general 3 manifolds. So I'm out of time, so I'll stop there and leave it to questions.